2011 E&M number 2. This is a circuit where we have a 9-volt battery, 500 ohm resistor, 25 millifarad capacitor, and if we connect the switch to S1, the capacitor gets charged up. Then we can connect it to S2 and discharge the capacitor through the inductor. We did not have a chance to discuss LC circuits to see how that goes, so I'll have to discuss it now. But starting with part 1. So we're going to close the switch to S1, and the current is going to go through the resistor and then deposit charge on the capacitor. Kirchhoff's loop rule says we go up the battery, down the resistor, and initially there's no voltage across the capacitor, so the resistor gets all of the voltage drop, and eventually that will switch and the capacitor will have all of the voltage drop. So for part 1, eventually we will have the charge on the capacitor equal to the battery times the capacitance. So eventually that will be 9 times 25 milli, which is times 10 to the minus 3, which gets us 0.23 coulombs. Now, pay very close attention to the bottom plate. Well, that long line up there is a positive and the short line is a negative. So the positive charges are coming around and the positive charges are being deposited on the top plate, which will then repel a positive charge from the bottom plate, leaving a negative charge on the bottom plate as the positives then move into the negative side of the battery. So what we need to do is we need to have a negative sign here to indicate that the bottom plate of the capacitor is a negative charge. All right, part 2. At T1, we close the switch. Well, before T1, until T1, there is no charge. And then starting at T1, charge builds up, and they want the magnitude of charge. So this is now going to be positive 0.23 coulombs, and this is going to be a 1 minus exponential decay, and it will reach 0.23 coulombs asymptotically. They do actually want you to label this. They do explicitly label any numerical values. Okay, so they want that. Down in part 3, again with numerical values. Also, until T1 there is no current. And then at T1 it jumps up to its initial value, and we will need to find that. So coming back up here to the circuit, we have 9 volts, 500 ohms, and that's going to be 0. So for part 3, Kirchhoff's loop rule, remember that guy. Going to have battery minus resistor minus capacitor gets us 0. Now that's for any time t. At time 0, that guy's 0. This is the battery of 9 volts. This is current and 500 ohms. So the current is going to be 9 over 500, also known as 0.018 amps. We need to have this value here to satisfy their requirements of having a numerical value. So 0.018 amps, and then we will have an exponential decay that heads towards 0. Now I'm going to have to pause and clear this out so I can scroll down to page 2. Alright, in page 2, part B, now we're going to uncharge it, we're going to recharge it, and then we're going to flip the switch to S2 when the magnitude of the charge is 105 millicoulombs. Okay, so how much energy is stored there? So B part A, energy is 1/2 CV squared, which is also Q squared over 2C. And hey, they gave us Q. So that's why I'm switching over to Q squared over 2C. So 105 times 10 to the minus third squared, 2 and 25 times 10 to the minus third. Gets us 0.22 joules. All right, part 2, maximum current. Now, those of you in mechanics, we did discuss this. Let's pause our E&M for a second and let's take a look at a swing or a pendulum. So in mechanics class, we did this lab. If you've ever been to a playground, you've seen this. Pull a swing to the side and then let it go, and swing just automatically goes down up to the other side, stops, turns around, and comes back. And it just keeps going back and forth. And yes, I know in real life you have to pump your legs and sway your body back and forth to go back and forth. And my 2 older boys just figured out how to do this. They're very proud of themselves, and they will sit in our backyard swing and just swing back and forth for an hour at a time. Over here on the left at the beginning and way far on the right at the end, the swing has potential energy, and it has potential energy here. Here in the middle at the bottom of the swing, when the angle is with the vertical is now 0, and it's moving really fast, and it's not going to go any lower. So for all practical purposes, here's the floor. All of the energy is kinetic. So the potential energy turns into kinetic energy, turns into potential energy, and then turns around and comes back and becomes kinetic, and then you're back at the beginning of potential. Now, this is a mechanical analog for what's going electrically here. So electrically, we have a capacitor that is fully charged initially. So we've got pluses here on the top and minuses here on the bottom. And then we have an inductor. So that, remember how inductors don't like change. So whatever they were doing before, that's what they want to do now. So initially there's no current, and this first charge jumps off of here and tries to go through here, and the inductor says, I don't want it. But then after a time, after a current has been built up, so over here effectively we have potential energy, and then after a time the current has been built up, and now we have current going through the inductor, and that's analogous to kinetic energy. Well, once that current is fully built up, that means that there are no charges left on the capacitor. The capacitor has been cleaned out. But the process of cleaning out the charge from the capacitor has been what builds up the current in the inductor. And now what's going to happen is that current in the inductor is going to slingshot extra charges around, and the capacitor is going to end up charged upside down, where the positives are on the bottom and the negatives are now on the top. And, oh man, those things got connected to each other. I was hoping that wouldn't be the case. And then what's going to happen is those positive charges are then going to build up a current in the opposite direction in the inductor, and they will come around and they will end up being on the top. So these negatives will turn back into positives, and those positives across the bottom will turn back into negatives. And effectively what we have here is the electrical version of a swing, where you can see we start out with potential energy on the left, swings through, now we have kinetic energy, and then ends up with potential energy again, but mirrored on the opposite side. So we start out with potential energy, end up with kinetic energy, and then we end up with upside down potential energy. That's what's going on here. Now, the potential energy for the capacitor is Q squared over 2C. The kinetic energy for the inductor is going to be 1/2 Li squared. Again, remember L is sort of like mass, and current, being the movement of charge, is a lot like velocity. So this is actually very close to being kinetic energy of the individual charges. So let's take a look at B part 2. Calculate the maximum current that will be present. Well, what we're going to do is say total energy original is going to be total energy final. And originally, it's the energy in the capacitor. And at the end, it's going to be the energy in the inductor. Well, we have a number for the energy in the capacitor. And we got that using Q squared over 2C. And now we're going to get the energy in the inductor using 1/2 Li squared. So I is going to be, let's see here, that'll be Q square root of 1 over LC once we separate everything out. And that will get us a current when we plug in those numbers of 0.30 amps. And that will be Imax. All right, B part 3. The rate of change of current when the charge is 50 millicoulombs. All right, 3. Here we need to go back to Kirchhoff loop rule. So when we have 50 millicoulombs on here, we will have a certain voltage across the capacitor, and that means that we will also have to have the same voltage across the inductor in order to have conservation of energy. The capacitor is Q over C, and the voltage of the inductor, remember, is L di dt. And time rate of change of the current. Okay, so rate of change in time of the current. That's di dt. That's what they want us to solve for. So di dt is going to be Q over LC. Hey, they told us what Q is, and they told us what, let's see here, where is that? We have to go back to the diagram. Yes, we do. L is 5 and C is 25 milli. So we can plug those numbers in. Oh, wait a second. We need a minus sign here. Yes, that's minus. And then this guy is itself having a minus. So we're going to have a minus there. Remember, the inductor opposes the change. So we're going to have to subtract the voltages to get back to 0. But this minus sign is part of the Kirchhoff loop equation. And that minus sign is tied to the fact that we're looking at an inductor. Sorry, I should have put that in there first. So minus 50 times 10 to the minus third. L is 5 and C is 25 times 10 to the minus third. So di dt, don't drop the minus sign, is minus 0.40 amps per second. Since that's a numerical answer, don't forget the units.